Hello and welcome back to a new video about measure theory. And as always, I want to thank all the nice people that support this channel on Steady. In this and in the next videos, I want to talk about so-called outer measures. And with this topic, we come back to the foundations of measure theory. In fact, after using Caratero-Dory's extension theorem many times, I now want to actually prove it. In order to do that, we need some suitable tools, and we find out that the outer measures are indeed these important tools. For this reason, I can tell you that for understanding the idea of measure theory, you don't really need the outer measures at all. But if you want to go into the technical details and maybe prove such an important theorem here, then you can't avoid the outer measures. The name comes from the circumstance that one wants to approximate a set from the outside, but we will talk about this later. However, in this context I should emphasize that both words here are connected. Outer measure is indeed a new notion. What I want to tell you here is that outer is not an attribute for measure. In particular, it's important to note that outer measures don't have to be measures in the usual sense. With this heads up at the beginning, I can however reassure you that the construction of such outer measures is not so complicated at all. Basically, I would say it's even easier than for the usual measures we had before, because we don't need a sigma algebra at the beginning. Okay, I don't want to keep you in suspense any longer, and therefore I present now the definition. Not so surprising, also an outer measure is first of all just a map defined on some subsets of a chosen fixed set X. Indeed, admissible are now all subsets of X, and therefore we can choose the power set. And for the values we are already used to choose the non-negative numbers where we include the symbol infinity. Now, such a map, which I now denote by phi to distinguish it from a normal measure, which we would denote by mu, is called an outer measure if the following three conditions are fulfilled. So please don't forget that we always want to generalize or abstract how the normal measuring of volumes in space would work. Therefore, we would never demand any crazy properties from this function phi here. Hence the first property you already know: if we put in the empty set in the map, we must get out 0. The empty set should not have any volume. Also, the next property makes sense in this picture if we look at a subset A of another set B, and maybe we visualize that first here in the picture. So we have the set X, we have a subset B inside of this set, and there also a subset A inside of B. What does this mean for the volumes? Of course, the volume of A should be smaller, or in the best case the same as the volume of B. So we have here less or equal. And that is what we call the monotonicity of the outer measure. Please note, this property we also had for an ordinary measure. It was just something we didn't demand in the definition because it followed from the other properties. And now the third property is something you might also recognize. Let's take a sequence of subsets, so let's call them A1, A2 and so on, from the power set of X. And for this sequence then holds that the union, measured with our map phi, is smaller or equal than when we add up all the volumes separately. This is now something that we also can easily visualize in this picture here. So if we form the union of both A1 and A2, we calculate the area here, which is of course smaller than adding the volume or the area here for A1 plus the area of A2. Simply because we add this intersection 2 times. You see, we don't need disjoint sets here, which means we can have intersections and they occur on the right hand side. So in general, we will have an inequality in general here. And because we have it for countable many subsets, you see we have an index in the natural numbers n here, we call it the sigma subadditivity. And that is all we need to get an outer measure. When you see these properties, you might think this is indeed a good substitution or abstraction for measuring normal volumes. However, you already know that this can't work for the whole power set if you consider the important Lebesgue measure. And you also see here in part C that we don't have the equality if we consider pairwise disjoint sets, something we usually call sigma additivity. Hence, a natural question here is, if I start with an outer measure phi, how do I get an ordinary measure mu? Or in other words, how do I get also for the map phi the sigma additivity? And we already know this won't work for the whole power set. Therefore, the first thing we should do is to restrict the sets we consider. And this leads us to our next definition. We only want to look at some good sets that we can measure, and in the end they will form a sigma algebra again. And the name for such a good set is phi measurable. And we use that name if for all other subsets, and now I choose the letter Q for another subset, we have the following additivity rule. The best thing is again to visualize that in a picture. So there's a set A, and here's another set Q. Now the set A splits this set Q into two parts, the one inside A and the other one outside A. Or by using formulas, here we have the inner part and here we have the part outside A. And now we measure both sets by using our map phi and add them up. And now we would say this measurement is meaningful if we get out the measure of Q again. This means that we call a set A phi measurable if it's so good that it divides every other set Q into two parts, such that there our map phi is indeed additive. Obviously, this is the first step to the sigma additivity we want. Now what I really should add here is that in some books you might find the definition as greater n equal. The reason for that is that it does not make any difference at all, because for an outer measure you have the other inequality here in the definition. Hence you could define it in this weaker sense, but still it means the same thing. Well, let's end this video with some cliffhanger, but of course I will go into more detail in the next video. The important proposition here is written in the following way. If we have an outer measure on the set X, then the collection of all these good sets here, and let's call them A with index phi, forms a sigma algebra. Of course, that makes our good sets even better, because this is the first part we need for our measure. In fact, if we define a map mu on the sigma algebra A phi, and how can we define it? Very easily, we just use our phi from before, so we have mu of A is the same thing as putting A into phi. And what comes out is a beautiful measure. So you see, this is indeed a very nice result. And then in the next video, I will show you some examples of outer measures, and then you will see that it's not hard at all to construct them. In addition, this proposition then will help us to get out an ordinary measure as we want. And of course, if you are interested, we will also prove this proposition. Okay, thank you for listening and see you next time. Bye!